Our second case is the flow on a slope, or you can say a open channel flow, right? Of course, we are not dealing with real open channel now, but this is a really simplified case. I think this case you are also familiar with from the fundamental course. So we have a slope here, and water is here, right? So the water here, the water surface is open to the atmosphere. So the pressure on the surface will be atmospheric. Let's call it to be P0. So we call this direction to be the x1 direction, here x2. This angle, we call it to be theta. Here, gravity takes a part, right? In the last case, we didn't calculate gravity, but now gravity is actually the propulsion. So obviously, we cannot neglect the gravity here. In the x1 direction, well, what's the component of gravity in the x1 direction? It's called rho g sine theta, right? What's the gravity's component in the x2 direction? This thing is called minus rho g cosine theta, because this part is to the up, right? We know g is something like this. Okay, so we can write out the NS equations. NS equations in x1. If we simplify things, well, obviously we need to first write out the continuity equation and make one assumption to get another simplified condition, right? Suppose we have done that. And what shall we get? What would we get? We would get that the flow is fully developed, right? And also it's one-dimensional. So that means one-directional. So it means the flow here only has a velocity component in the x1 direction, which means we only have u1 here, but we don't have u2 here. Also, the flow here should be fully developed. That means du1 dx1 is equal to 0. So suppose we have gotten that, okay? With those conditions, we can simplify the NS equations. Suppose we had done that, and we would get something like this. dp dx1 plus rho g sine theta. Well, the NS equation on the left-hand side will be 0 again. Plus mu du1 dx2 squared. This thing is equal to 0. Here we can write out the NS equation in the x2 direction, because here we also need to solve for the pressure, okay? We are given a boundary condition regarding the pressure. dp dx2 minus rho g cosine theta. This thing is 0. What will be our boundary conditions? First, we have a no-slip condition, right? u1 at x2 equals to 0. This thing is just 0. Do we have another boundary condition? Yes, on the water surface, right? What's the boundary condition there? Here we need to make the assumption, although this is also true in the real case. The viscosity of air is very, very small compared to the viscosity of water. So the shear stress applied by the air on the water surface can be neglected. So here we can say tau to 1, right? On this surface, this is the surface that is perpendicular to x2. So the first index is 2, and on the pressure, the shear on the water surface, the shear stress is pointing in the x1 direction. So this shear stress will be called tau to 1. Tau to 1 at x2 equals to h. At x2 equals to h, right? Will be 0. And we know how to calculate the tau, right? This is a component of the tensor, of the stress tensor. So this will be something like this. This thing is equal to 0. du2 dx1, u2 is 0. Or you can say everything derivative respect to x1 is equal to 0 because of the flow is fully developed. Anyway, we get this, right? So with the two equations and the two boundary conditions, we can solve for both the p and the u1. If we solve it, we will get the result. P is equal to P0 plus rho g h minus x2 cosine theta. You can check my result. U1 is equal to rho g sine theta over 2 mu h squared 2 minus x1 over h, x2 over h. We can see the U2 here has a parabola profile, right? And when is the velocity the highest? It's at x2 equals to h. You can check that.